Hello, my name is Patricia Pedraz and I'm doing my PhD at Nanoscience in Madrid, Spain. Friction and wear are subjects of enormous economic importance in all areas of daily life and industrial production. In this paper, we investigate mechanisms of wear on the nanoscale using scanning force microscopy, and in particular the suppression of wear by ultrasonic vibrations. This study centers on the formation of ripples underneath the tip of an atomic force microscope on surfaces of compliant materials such as polymers. These ripples can be considered a pre-stage of abrasive wear in many cases. Ripple formation as a pre-stage of wear is also observed in many cases on the macro scale, for example on roads, rails, and other surfaces. We ascribe the formation of ripples to a stick slip mechanism, which we can model empirically. That means without addressing the underlying microscopic processes for a specific material. In the experiment, we mount a substrate with a spin-coated polymer thin film on a piezoelectric transducer, which vibrates the sample in the vertical direction. Since the amplitude of the vibrations is very small, we employ the so-called contact resonance for the amplification of the vibrations. The contact resonance is the resonance of the cantilever with the tip in contact with the sample. The frequency and width of the resonance depends critically on properties of the sample, the normal load, and the excitation amplitude. We found that out-of-plane ultrasonic vibrations can strongly suppress ripple formation if the vibration amplitude is sufficiently large. Ultrasonic vibrations reduce such wear of the surface by facilitating a slip in each retracting phase of the vertical vibration. In addition, suppression of wear may be aided by the so-called strain hardening. That means a hardening in the plastic region of deformation, at large deformation and for high deformation rates. It is interesting that ultrasonic vibrations applied to the tip of the scanning force microscope or to the sample allow to reach deformation rates beyond those accessible by typical engineering experiments on the macro scale. Wear of compliant materials implies plasticity. The plastic response of the samples must be studied as a function of specific material properties, including the presence of side chains, the molecular weight of the polymer, and the solvent content, as well as a function of temperature and deformation rate. A detailed study of wear on the nanoscale and its suppression by ultrasonic vibrations will be of enormous interest for mechanical engineering, as it is expected to be relevant also on the macro scale. Here, it should be taken into account that the contact of macroscopic bodies is generally modeled as a contact of a large number of asperities of different sizes. Thank you for your attention.